This podcast is about using inferential statistics in political science research. Recall from previous podcasts that we use inferential statistics to make conclusions from the sample, and then we infer about the population as well. So we want to be able to use the information that we gather from analyzing our sample and generalizing to a larger population. An example: what of the population that lives under $2 a day in the least developed countries, or what are considered global south countries? Let's say that we have gathered information for 124 countries, and this will be our population of all countries around the world. So the population mean of those percentage of population that lives under $2 a day is 34.8%. Now we take a random sample of those 124 observations, let's say 10 observations, and that sample mean is 29.4% of the population lives under $2 a day. So the sample mean we can see does not equal the population mean. That's a problem because we use a sample mean as an estimate of a population mean. We generally have more access to information about samples than we do about the population. So we consistently use sample data. But sometimes the sample is just a little bit off from the population. And is that a problem? Well, how do we deal with the discrepancy between a population and a sample mean value? One way to deal with it is to use something called the central limit theorem. And if we take an infinite number of samples from the population, most of the time the sample mean is going to be very close to the population mean. So if we randomly sampled 10 countries 5 times, then this table on the right-hand side tells us what the mean value for the percentage of the population that lives under $2 a day is in that small sample. So we can see 29.4 for sample 1, 37.1 for sample 2, 41.2 for sample 3, 32.7 for sample 4, 33.1 for sample 5, all randomly generated samples from that larger population. And the population mean, again to remind you, is 34.8. So 34.8 is relatively close to each of those small sample values, small sample mean values. So the central limit theorem tells us that, generally speaking, most of the time the sample mean is going to be very close to the population mean. So that's one way to deal with the discrepancy between a population and sample mean value. We can also use what are called confidence intervals. We use the sample mean and the sample standard deviation to estimate a range of potential population mean values. So the idea is we want to have what is just by custom 95% confidence that the true means of our variable lies between a lower and an upper bound. So if we do this confidence interval calculation on our data, we have a 95% confidence that the true mean of our poverty variable lies between 11.1% and 47.7%. If we had to take a guess, it would be close to 34.8%. So that would be using confidence intervals to allow us to have some confidence that our sample mean is close to our population mean. And that's using confidence intervals to do that. Now, what about making conclusions about the relationship between two variables in the population? Well, one powerful inferential analytic technique is called regression. Regression will give us the equation for the linear line that goes through the middle of the data points on a scatter plot. And that equation looks like y equals b times x plus a, where y is the dependent variable, b is the slope of that line that we draw through the data points, x is our independent variable, and a is the y-intercept, or where the line crosses the y-axis on a scatter plot when x equals 0. And we'll go through what all of this means. So to go back to our data example from our previous podcast, we're going to use the same one, where GDP per capita is the independent variable along the x-axis. Net migration is the dependent variable along the y-axis. And we hypothesize that the greater the GDP per capita in the country, or the wealthier the country, the greater the net migration into the country takes place. So that is our hypothesis. And remember that we put a line through these data that suggests that there is a positive relationship between the two variables. So that would tell us that as GDP per capita increases in value, the net migration also increases in value. We can get very precise about these things too. The slope is simply the change in y over the change in x. So the change in y involves us looking at just how much the data points deviate in terms of the vertical changes that take place. So you can see from the example, the green points show the change in y. The blue show the change in x, or what is sometimes called rise over run. The rise is the y, the run is the x. The intercept is where the value of y what is the value of y when the line crosses the y-axis. In other words, where x equals 0. And so we'll be able to show this all numerically. If we just do an equation and estimate an equation, this regression analysis will show us that the y-intercept is around 182,752.154 minus. It's a negative number. And the slope coefficient is 19.045 multiplied by GDP per capita. So that means for every unit increase in GDP per capita, migration increases by 19.045. So that's a very precise result. I'll go back to it for a moment. It's equivalent to y equals b times x plus a. Although here, because the line crosses the y-axis where x equals 0, that y value is actually a negative value. So that's why it's a negative sign. B, or the slope coefficient, is the key to the analysis. If the slope is positive and statistically different from 0, that means that the slope is positive. In other words, as the independent variable increases in value, the dependent variable increases in value as well. If b is negative and statistically different from 0, then that means the slope is negative. Or in other words, as the independent variable increases in value, the dependent variable decreases in value. If b is not statistically different from 0, it means that b could be positive, the slope coefficient could be negative, positive, or 0. We do not know. So there's a fundamental distinction between being statistically significant and not being statistically significant. It's very important for regression analysis. So what does it mean to be statistically different from 0? If b is not statistically different from 0, it means b could be any value at all, positive, negative, could even be 0. If b is statistically different from 0, we are concluding that b is so large or so small that it is not by chance that it is that way. It really is, in truth, larger or smaller than 0. So statistically different and not statistically different have fundamentally different implications for the conclusions that we make about our data. So it's very important to get those correct. When we read regression tables and articles, the tables will list the dependent variable and the independent variables. They'll also list the slope coefficients, the b's, for the independent variables. And the table will usually have some asterisks or stars next to the b's, and those stars indicate, or asterisks indicate, statistical significance. So if the b is in the correct direction as expected based on a hypothesis, and the b has a star next to it, then b is statistically different from 0 in the way that the author expects. The author thus has support for their hypothesis. Otherwise, the author would not have support for their hypothesis. So for example, parties in countries with bicameral legislatures or two-house legislature adopt more stringent candidate selection procedures than parties in countries with unicameral legislatures or just one house. So we can test that hypothesis. And in fact, it was done in a recent article. And if we look closely at the box, the rectangle box of 1.450 with 3 stars above it, what that indicates is that the slope coefficient for the independent variable, bicameralism, is positive. The stars indicate statistical significance. Thus, indeed, we can say that candidate selection is more stringent in countries that have bicameral legislatures, two-house legislatures, than if they have not two-house legislatures or one-house legislature, unicameral legislature. So the stars indicate that the B is positive and statistically different from zero as expected. The authors thus have support for their hypothesis. This is how you read a regression analysis table and a social science article. And that concludes this podcast.